Today we're going to look at the lecture for week 5. If we look at our home page here and we navigate to the schedule, the thing we're going to be talking most about this week is memory. We're going to touch on a few other issues that have to do with the problem sets this week. So let's dive right in. You can access the lecture slides as usual with this little computer icon that links. If you look down in the well, my inset is hiding the whole path, but you can see that it links to the slides that are down here, where my cursor is, just to the right of my shoulder. If I mouse over the one, you can see it's slides 5. We're just going to go straight over to them. Here we go. One of the first things we're going to talk about is how computers store pictures. And this is a picture generated by AI of pyramids, possibly in Egypt. I don't want to infringe on any cultural heritage issues here. And a rubber duck. This is quite a nice image because the clouds are reflected in the water. Yeah, and there's good sunlight shining from the top right onto the duck and onto the pyramids. Yeah, I like this image a lot. But, you know, how do computers store the data that make an image like this? Well, there are different file formats. There's JPEG, and there is TIFF, and there is RAW. But we're going to just really go to the simplest format and talk about bitmaps. And bitmaps are just a series of pixels, and each pixel has data associated with it. And what is a pixel? Pixel's just a square. So why don't we see the little squares that comprise the whole image? Well, if we zoom in just a little bit on the duck, we can start to see, maybe the video resolution is good enough for this, we can just start to see the edge of pixels. Sometimes we refer to seeing those edges as being pixelated. And the more we zoom in, the more we can sort of see the individual pixels. And in this PowerPoint slide, we don't see the individual pixels very well. They're kind of blurry, and this is a trick that some computer programs do to display images that aren't very good resolution. But I mean, if we zoom right in, you can actually see that there is a grid of individual colors, and each grid is just a single color. And it's when we zoom out that we start to, our brain starts to make it look like a very smooth image. So what is the story with these individual pixels in a bitmap? Well, we can think of them like just a series of zeros and ones. It's not quite that simple, so this is really going super simple. And you know, we can map the bits. A bitmap, .bmp kind of file, kind of image, is literally just a map of bits. Now, maybe you can look at this picture and you can see that it actually does make the picture of something. You know, can you see it? What is this image depicting? I'm just going to rearrange one of my screens on the left. You might be able to see that the zeros actually create an image. What is it? It's a smiley face. Bam. You know, you can see that if we add the grid back and kind of look at how this might be mapped onto an image, it might look something like this. And it's through very, very simple arrays of data like this that we create, you know, what a lot of people might call pixel art. And pixel art, there are specialized programs that make it, but this is one of the just simplest kinds of images that you can make with computers. And, if you're like me, you might find it very fun to mess around and create your own pixel art. You don't need a fancy program, although these days it's quite easy to have access to fancy programs. But actually, making pixel art could be done in Microsoft Excel or an open source equivalent. You could just make grids, and you can change the colors of the cells on a spreadsheet to create quite complex art. And this kind of image drives a lot of creativity in the history of computing up to the present day. Some people, you might even find people that refer to themselves as pixel artists. So here's an example of pixel art that is an homage to Super Mario Bros. And, we might make an homage to our Scratch days with a pixel art of the Scratch the cat. Or you might make, pixel art of, your favorite sport. Maybe it's rugby, maybe it's American football. Well, I'll never tell. And, we can also have fun with individual pictures that are scaled down just for fun to make pixel art that's describable like this. If you've heard of NFTs, how much would you give me for this one? So what I want to talk to you about really on a swinging, the idea of how computers store data for images is the idea of red, green, and blue, RGB, how an array of complicated colors are stored. And we're eventually going to get around to talking about the specific storage format for RGB colors in modern computers. So what is this? This is a color picker window for a popular program that many of you probably have used called Photoshop. Now, what do we see in here? Well, see quite a lot of busy stuff going on in here, but I'm just going to ask you to focus on a couple of the different fields that we see. One, we have this big field that has an array of colors in it, and this is on a scale from black to white to red over on this top corner, and we can use the spectrum picker on this side to change the spectrum of the color. Over here we have a little window that depicts what our current color is and what the one depicted in the color field to the left is, which would be our new color if we select it. You can just see the outline of the cursor down here that's selected this all black, 100% black color, and you could choose that. Now down here amongst these little windows and radio buttons, we have an array of different ways to display colors, CMYK, HSB, LAB, but we're actually just going to focus on this one down here, RGB, okay? And RGB stands for red, green, blue. Turns out that you can display a really large amount of colors with just different pixel values for red, green, and blue. If you adjust the amount of red from 0 up to some number, you can combine the red, the green, and the blue to make a large array of colors. And there are different schemes for this, all of which are translatable to one another, but like I said, we're going to stick to red, green, and blue for now. Now, this one depicts black, as we discussed. You can see a picture of it up here. But down here is this little pound sign, and it's 6 zeros. What does that mean? Well, this is a representation of red, green, and blue, the red, green, and blue content specifically in this chosen color. And there's each two spaces. Let me just move on to what I'm going to say before I get into the two spaces part. What do you think that that an all white color would be is the next thing that I want to say, and how the cursor would change. Well, there's a little bit of all white just up here at the count, but what do you think it would do to the values in the RGB here and to this pound sign color? Let's see. Well, what we can see is that now we've chosen white on the color field. We've got white as our new potential choice, and might have imagined that there would be some numbers here, but it's F's. It's all F's. And what we can see now is the values of R, G, and B have changed from 0 to 255. We know that white is a mixture of all the colors combining to be a very bright white field. And in the RGB world, 255, there's 256 possible values for each of these primary colors, and that goes from 0 to 255. So here we can see that R, G, and B are all at the max. Now, what I want to look at here is what these F's mean. We're eventually going to swing around to it, and first, though, I want to show you, well, what would a red field, a pure red field, look like? Well, we can choose that on here. By choosing red, see the window changes, and here we see there's 0 green and blue, and it's 255, the max red. Look how this changes. Now it's FF0000. And what about green? Well, we could change green on the spectrum picker here, go up to the all green corner, and now we have 00 FF00, and up here in the RGB we see 0, 255, and 0. So what we're kind of seeing here, what we can figure out given the information so far, is that this is a 6-digit representation of some values, and that 00 indicates absolute 0 for red, and the third and fourth characters here are FF, which indicate the maximum value for green. So we're seeing a kind of different scale that we haven't seen before. Now the scale is called hexadecimal. If we just, for completeness, look at blue, we can see how that changes, 00255 and then 0000 FF for the hex notation. So what is this FF? Well, we know about binary that can take on the values of 0 and 1. We talked about that quite a lot in the first couple of weeks. We know about decimal that has a base of 10. This is the kind of number system we use all the time every day for mathematics, and that goes from 0 to 9. But I used the word hexadecimal. What the heck does that mean? Well, in hexadecimal notation, this extends the number values past 9, and instead of displaying the number after 9 with a 10, which, you know, there's some ambiguous bits about displaying a 10, but also it requires 2 character spaces. And so someone thought, oh, well, why don't we extend the bases to a 16 system? The choice of 16. Why 16? Well, I'm actually not sure. If one of you know why they chose base 16 rather than base 18 or something different in the beginning of computing history, hey, let us know in Discord. I'd love to hear about that. But nevertheless, they did choose base 16, and they've extended the first 10 characters from a decimal system by 6, and they chose to represent these by A, B, C, D, E, F. This is a single space for 16 characters from 0 to 15. So these letters represent the numbers 10, 11, 12, and so forth. Well, yeah, we could also use lowercase for them. And, you know, this comprises the hexadecimal system. I've used that phrase, and that just means, you know, base 16, which I've also used. And this is a, you know, so you're not surprised. This is a way, like binary, that uses zeros and ones. The base 16 system uses those characters from 0 up to F, okay? And so it works just like the binary system, where we're going to count in hex to make some numbers, where we have, let's say, the 2 spaces that we saw in that color picker. And we can create quite a lot of numbers with just these 2 numbers going up in the hexadecimal system. Now, if we wanted to create some numbers, what we'd have to do is we'd have to think about, well, what's a specific number down here that's 2 digits that we could create with the bases 1 and 16? Well, if we wanted to create 0 and 0, that means we would have 0 ones and 0 16s, and so this would evaluate to a complete 0. If we wanted to evaluate 1, you know, we'd have a single 1 in the 1 space and 0 for the singles. And you know, we can continue to do this. This in hexadecimal would be 2 1s, 3 1s, 4, and so on. When we get to 9, what do? To represent 10, to evaluate to 10, we switch to the letters 11, 12, 13, 14, and 15. Okay, so what do we do when we get to 15? We've done 0 to 15, so 16 characters so far. Similar to binary, the way we would represent 16 in hexadecimal is like this, with a 10. Now, this is potentially confusing, because 10 is not 10 in the decimal system. It's 10 in the hexadecimal system, and this set of characters in hex, 1 and 0, evaluates to 16. Of course, we can keep going, 11, 12. Each of these represent 17 and 18, respectively. Why? Because we've got here, why is this 18, 1 and 2, 18 in hex? Well, we've got 1 16 and 2 1s. That evaluates to 18. And we can keep going as long as we want. Now, what's the highest number that we can count to? Can you guess? Well, in fact, I already told you. We know that the highest we can count to is FF. And what number does that evaluate to? Well, we can do a little bit of modest math, and we can say that, well, there are 15 ways that 16 will be represented, cycling through all the values of 1, and then the 1 space can take on the 15 different non-zero values, and we can just evaluate that out and add it up to come up with 255. So that checks out with the RGB system that we were talking about. So why is hex so popular? Well, it's popular because it can condense the amount of information stored to a smaller space. This was probably conceived back in the days when memory for computers was a lot less plentiful than it is now, and it's very plentiful now. It's not unlimited. That still is an issue for pipelines that require a lot of data all at the same time. It, just for example, it's an issue in the training of artificial intelligence large language models. We hear about that sometimes, about the about the amount of parameters in one of these large language models, and they're getting bigger and bigger, which guess what, requires more memory. If you're into video games, you'll be aware that a $300 pound laptop from Amazon probably won't play all the video games you might want to play very well. Why not? It doesn't have, well, two reasons really. It doesn't have a dedicated graphics processing unit on a video card, but also because it doesn't have any dedicated RAM to run video games. It doesn't have any dedicated memory to do all those calculations for a video game. And so anyway, this kind of notation is still popular and relevant because of that. And we have these values. We can think about literally how much memory they take up, and we might think that each one would take 4 bits to represent. Can actually represent a whole byte with just those 2 hex digits. So that's why it's very popular. It takes up less memory. And we can kind of get explicit about this with our theoretical model for memory here. Remember this grid? We remember that each of the squares represents a space in the physical memory on a RAM chip, perhaps, and we can enumerate the the spaces from 0 to 16, and we can store in them the characters from 0 up to big F, and we can keep going like that. Now, I mentioned this before, but as we go beyond, F, and we start to put things in hexadecimal notation, we've got this this big potential for ambiguity, because 14 just looks like the decimal number 14, but it's actually the hexadecimal number 20 on this slide. How do we tell the difference? Hey, we've got a solution for that. We usually denote hex with starting a hex representation with 0x. This is just a little note that is appended to the front of every hex expression that denotes the use of hexadecimal. Okay, this is a way to communicate it outside of the computer world, to communicate about hexadecimal. Now, one of the things you're going to want to do is, like a lot of the other lectures, I'm not going to explicitly run code. Somebody, if one or more people would like me to do that, you can let me know, and I'm willing to do that. But for now, I'm not going to do that today. Instead, I'm going to assume that you're watching this video to get the idea, and probably then you're going through the notes and you're running the code that is gone through in detail in the notes. And not only that, probably for most people, you'd probably be better off by typing all of the little scripts and programs that are mentioned in the notes manually, for the reasons that I've expressed several times, that you learn from your mistakes, and you practice in your typing, and you get that muscle memory for certain patterns and expressions in any programming language, and in the use of the terminal. However, if you run into a problem and get frustrated, you can always check out the code files, and for this one you're going to want to check out addresses. There are several versions of it that follow along with the notes, so check them out. So what are we doing here? Well, we're going to talk about how, switching topics just a little bit, how memory is actually stored and addressed in computer memory. And, maybe we have a little bit of code that is like this, where we've declared and initialized some integer value, which we'll call n, to the value of 50. So let's think about this value and think about, how would this be stored in a block of memory like this? Well, it turns out that memory is allocated in in the computer world in an arbitrary way with respect to, let's say the space, the actual physical spaces on a chip. So that 50 might be placed down here at this arbitrary block of memory. We're taking up 4 bytes of memory, like normal for an integer, for a regular integer, and we've called the name of it in. Now, we talked about this idea of addresses for memory like this, and we've talked about it usually with metaphors. The metaphoric way we've referred to it is, we've talked about it like mailbox boxes, and, inside the box is the value that we're storing, and the box itself has a number, and that's how we find it. And we've played with this in past weeks a little bit. Today we're going to bump it up a notch, and we're going to suggest that, actually the physical address on memory is stored in hexadecimal format. And that's what we're going to talk about for most of this lecture, actually, is about how memory is stored and how to manipulate memory in different ways.